Okay, right. We'll start here. So, seems like we only have few students here. That's going to be a problem if you are going to continue doing this. So, you see. So, we'll start with a small question. Now, we last week finished aldehydes and ketones. So, we will start with a small question here. I want you all to produce this with me. Can you produce that? It's a bit of a multi-step process, but I'm pretty sure you will be able to get to the answer here. All right. If you're done, let me know. Students, bear with me just a second. I'm sorry. I think I did make a small mistake. There should be OH here. There should be OH there. Did it make it any easier? Okay, I think we'll discuss now. So here you can see this is carbon, only 3 carbon atoms. Here we have 3, 4, 5, 6, 7. And this seems like a group that we easily can get. I don't know whether you remember. When we are adding a cyanide group to a ketone or aldehyde, what happens? You add a CN and a OH to the carbon bearing the carbon oxygen double bond, or carbonyl carbon. And then if you add acid and heat it, or if you add H plus and water, what happens? The cyanide group turns into carboxylic acid group, right? I have given that note last week, if I'm not mistaken. So if you can see it that way, now students, you will see this only when you are associating this material a bit more than, like, just once a week. If you come and see these type of questions only once a week when you're having a class with me, it will be a problem, right? So first thing is we need to increase the carbon chain's length. So we do self-condensation reaction, or we say condensation. We have this. If you add sodium hydroxide, NaOH aqueous, what happens is we have this self-condensation of this ketone. So you remember, alpha carbon has hydrogen that can be removed in the presence of sodium hydroxide. So this section becomes negatively charged, and the negatively charged carbon goes and attack this carbonyl carbon of another carbon atom. And then this happens. CH3 is there, and this section, this carbon is getting attacked. So then therefore this oxygen becomes OH group, right? I will write this CH3 down. I will write this CH3 down because I want to write the rest of the molecule horizontally here. So then the alpha carbon removed hydrogen is this. So alpha hydrogen removed carbon is this. And then we have the rest of the ketone like so. right? Very simple, right? So we have this, and I would have also mentioned, if you put little bit of acid and heat, what happens is this will form a double bond also. I might have told you this earlier, but we don't have to do any of that. If you have OH group, we can convert the OH group into a Cl group. Easy. Can someone tell me the reagent that I need to have to do that? Help me out here. What do you do? What do I add here to get a Cl here? PCl5, right? PCl5. You have PCl5, right? Whenever you want to convert alcohol group into a Cl group, we add PCl5. Even carboxylic acid OH can be converted into a Cl if you add PCl5. We will be learning about it today. And then think I need to utilize, I will draw it here, okay? Yeah, I will draw it here, otherwise I will not have enough space. So to this I can add CN, right? HCN can be added, or potassium cyanide along with an acid. HCN can be added. So if I add HCN here, HCN, what is going to happen here is the CN1 minus ion can attack this area and form this CH3, CCl, CH3, CH2, COH, CN and CH3, and then we can turn this into an acid by adding H plus H2O. Okay, so that is how we can do this. Right, so is that clear now? Is it understood? There is a small problem though. This question I just made up while I was talking to you. When I was doing this, now I realize there's a small problem here. Can someone tell me what the small problem is? Now this question was something that I just made up. What is the problem here? I didn't see this part before I completed the conversion. What is the problem here? At least you have to be able to figure out the problem as well. Okay, there's a small problem in this conversion. Anyone? I will help you out. Cyanide group acting as a nucleophile, here is a problem. What is the problem there? Cyanide group, when it is acting as a nucleophile, there's something going to happen here. What is it? So I will show you how to do it separately as well. But what would be the problem? Students, can you remember alkyl halides also react with cyanide groups? Yeah, alkyl halides we did some time ago, right? So when you have a cyanide group, it can also interact with the alkyl halides, but you need something like KCN at that point, KCN and HCN together. But here there is a chance of even this group reacting with the cyanide and replacing a Cl with cyanide. Is that clear? Can you remember alkyl halide reactions? All nucleophilic groups can attack alkyl halides, and anything with a lone pair and anything that is a nucleophile, we see so many different reactions with alkyl halides and nucleophiles, right? Acetylide ions can attack, alkoxide ions can attack, cyanide groups can attack, right? So many different negatively charged groups can attack here. Hydroxide can attack and replace the Cl, right? So then it's not going to be that easy to just get the cyanide only there. So what you can do is, we can form the double bond here, and then we can, like, add something like peroxide and hydrogen halide addition to get the what do you call it, Cl group here in this carbon. So we didn't even have to add peroxide. We can just add HBr or HCl and directly get the halogen there after forming a double bond here. Is that clear? So yes, with that, if you want, I can show that to you. We can heat this, right? We can add H plus water and heat, H plus water and heat, and then you are getting this CH3, CH3, and double bond CH here, and then we have this CH3, right? And while keeping it this way, we can add HCl. Then we will get to this CH3, C double bond CH, OH, CN, CH3. From here onwards, if you add HCl, hydrogen will go here, Cl will go here. Right? Normally we always add HBr, but HCl also can be done. So H will go here, Cl will go here, and then you can add what do you call it, an acid. It will turn into that. Is that clear? So that is also possible. So I want to do a small exam question, students, that looks very simple. Can I erase this? Right. Quickly get this done. I will give you an exam question after this. Are you done? Can I give you a small exam question now? Now I will help you out a little bit here after giving you this. Now we are talking about aldehydes and ketones, right? So that's why I'm giving you this question. That's the help that I can give you. I'm talking about aldehydes and ketones. So I can tell you, that's why I am giving you this question. This is actually somewhat not as simple as it seems. There are many steps here. At least, bear with me, I'll tell you the number of steps. There's 1, 2, 3, 4, 5. So it has 5 steps. Okay. Is it simple? I would say not very much. I have told you the opposite version of it, how we can do it. Like if you have this, how to get it to this position. Right, that was easy. We have done that one. Right, that's about 3-step conversion if I'm not mistaken. That one is super easy. Sorry students, I need to bear with me. I gave you the question wrong. So I need to show the steps. Otherwise you will not be able to get to the answer, because there's other different method to get to as well. One, two, three, four, five. If you want, I can give you some help. Let me know. Should I give you a little bit of a hint? So the reagent here is Br2. Reagent here is HgSO4 and dilute H2SO4. I think now it must be clear. You need to complete the rest. I would say that's enough time. I will discuss this part. Can I? Right? So, first one, right? You at Br2, you form this CH3, CH2, CH2, but there will be Br connected here and Br connected here. Br2 brings two Brs there. Now, if you add Hg2 plus and sulfuric acid, you have gotten a ketone here. So what should be present here for us to add this reactant to get a ketone? A triple bond. Correct. So what we have over here is a triple bond. How do you get a triple bond here? How do you get a triple bond here? You can take this and you can take ethanolic KOH, ethanolic NaOH, either one is fine. Right? You get a triple bond. Now don't get confused. They do try to sometimes trick you a little bit. The triple bond is here, but now the ketone group is present here. It doesn't matter, students. Either way, what happens is when you add dilute sulfuric and HgSO4, what happens is we are adding a water molecule across this triple bond, just one water molecule. So for example, if you have, I will write the mechanism here for a bit so that you remember this, right? Instead of the triple bond, we will have a double bond here, and then we are adding a water molecule. A hydrogen goes to one carbon, the OH group of the water molecule goes to the other carbon. So hydrogen usually goes to the place where there is more hydrogen. So out of the two, hydrogen is more present more in this carbon. So the new hydrogen goes here. The OH group of the water molecule goes here. Right? What you produce here is referred to as an enol. Enol. The reason is the OH group is there, which is referred to as OL in this particular case, and there's a double bond, so therefore we call it ene, right? Double bond is represented by ene, OL is representing the OH. Is that clear? So enols are unstable. We learned about this. So therefore this get rearranged, like they rearrange the groups to form a keto group or an aldehyde group. We say actually even aldehyde groups are referred to as keto groups in this case. So it rearranges itself to form something a bit more stable, which is this. So on this carbon bearing the oxygen, there will be a double bond, and this double bond between carbon will be disappearing, and here this carbon will have three hydrogens at that point. So we will have a double bond here making a keto group here or ketone group here. So students, when you do that, on the second carbon we have a carbonyl carbon. On the second carbon, they have drawn it this way, like instead of drawing the carbon oxygen double bond here, they have drawn it this way. But if you count, it's on the second carbon, right? And they trick you. You kind of feel like everything was in this corner. How did it come all the way to this side? It didn't come to that side. It's the same molecule still. If you have the enol produced here, on the second carbon you can see there's a OH group. So this oxygen turns into a oxygen carbon double bond, and it is going to be present on the second carbon. Is that understood? So here you can see the carbon is on the second carbon. They have just tried to make it a bit more complicated. This is 2001 or 2002 question. So because of that, sometimes you might wonder how to keep shifting the carbon oxygen double bond here. You don't have to worry about that. If you know the chemistry behind it, it'll be easier. So I just want you to know this. When you add Hg2 plus and dilute sulfuric acid, first the enol will be produced. You don't have to show that. You don't have to show that. This is the mechanism. I'm just showing it to you so that you understand what's going on. This section is not something that you will write. This is a mechanism. So when you add this, you immediately get a ketone, and we need to have a double bond here instead of this carbon oxygen or carbonyl group. So how do you do that? How do you get to this? At least tell me that. What do you do here? This one is easy. Tell me. You have to tell me. You have to help me out. How do you get a carbonyl group to turn into a double bond? I was planning on finishing off carboxylic acid. I feel like I should go back to the basics again. How do you get a double bond usually, students? There are how many ways? The thing is, students, you are forward thinking, like in the sense, I am not meaning it in a good way. Like you can only think in forward direction, right? Some of you, not all of you. So that means you are starting here and trying to go only in forward direction. But you should be able to think backwards as well, a little bit. There's a double bond here. How can we get a double bond in a molecule? How many ways did you learn? Through an alcohol can we get to double bond? Yes. Why not? Right? Through alcohol can we get to double bond? Yes. How do you get to double bond? If you have alcohol OH group, we can add aluminium oxide and heat. Or you can add concentrated sulfuric acid and heat. A double bond will be formed. Or you can have a group like a halide group or halogen group. So if you have a Br or I or whatever it is, you can add ethanolic KOH, ethanolic sodium hydroxide. Then what happens? There will be elimination reaction, and then this whatever that is present here will be forming a double bond. Exactly. So through a like an elimination reaction of alkyl halide, we can get to this, or through a dehydration reaction of an alcohol, we can get to this. So we have we have a ketone here. We can easily make it a OH group by adding what? Lithium aluminium hydride, right? Ether, dry ether, and after that we can add water. So then what happens? CH3, COH, CH2, CH3. Now we have this OH group here, and then we can add anhydrous Al2O3, and we can heat it. So then we get to this OH group will be leaving with a hydrogen atom, but we remove a hydrogen from nearby carbons. Nearby carbon, here there's one carbon with 3 hydrogens, another carbon with 2 hydrogens. If we remove the hydrogen from the carbon that has the lowest number of hydrogens, out of the two, this carbon has the lowest number of hydrogens, we remove the hydrogen from that. Is that clear? So the double bond will be formed there. Is it understood? Okay. So simple tricks, students, you should be able to get to these kind of answers. I'm going to erase this part. This is not needed. I will teach you another thing after this. One more question and we are moving on to theory. I will give you more questions later on. So today afternoon session we will try to do as many questions as possible. Okay. So first of all we get through the theory parts. Write down a question. Write down a question. Show how the following conversion can be done. show how the following conversion can be done without the use of catalytic hydrogenation. Number of steps should not exceed 3. Number of steps should not exceed 3. Keep in mind, students, I am not giving you anything that I have not taught you by now. Okay? So if I am giving you this question, you have learned all the reactions that will lead you to this answer. So now all that you have to do is do this conversion, but without using catalytic hydrogenation. Catalytic hydrogenation means, students, where you put hydrogen gas and nickel or platinum, palladium, those kind of things, right? You can't use any of that here. Only it should be less than 3 steps, okay? Done? Very good. Correct. See, if you remember the steps, so you will, in the sense, if you remember what we have done in the past, you will quickly get to the answers. Okay, shall we? Right, now students, you can't use nickel, platinum, palladium and hydrogen, right? You can't do that. Can we use then any other catalytic hydrogenation, like for example palladium coated barium, barium sulfate deposited with palladium and then hydrogen? That also cannot be used, right? All those are catalytic hydrogenations. That means adding hydrogen to the molecule in the presence of a catalyst, right? So you can't do that. So then what can we do? You need to tell me the reagents if I want to produce this. Now I'll help you out. This is a two-step conversion. First step is this: CH3, CH2, C double bond O, CH3. Can someone help me and tell me what reagent I should be adding here? What is it? Yes, Hg2 plus, Hg2 plus and H2SO4, dilute sulfuric acid. Right, you get this. And now please look into your work that you have done and tell me how we conduct this conversion. It was taught to you not so long ago. Actually last week. What is it? Zinc in mercury, right? Zinc, we sometimes write like this, and concentrated HCl, concentrated HCl. So this section automatically becomes CH2. We are not adding hydrogen. We are not adding hydrogen molecules here. Do you see here? No hydrogen molecules. This is not a catalytic hydrogenation. Is that clear? This is a reduction. We learned it under reduction. So this section gets reduced to a CH2 group. So this is another method. So you really need to remember the things that we have studied. It will be easier for you if you remember these kind of parts. Okay? Right. So shall we move on to the theory parts, because I need to finish off the lesson. I'm planning on finishing off organic chemistry today, so hopefully we will be able to do that. So carboxylic acid groups related chemistry is not that difficult. It doesn't have we don't have a lot to learn here compared to the other parts. So we will take a new heading, a brand new theory part: carboxylic acids. Carboxylic acids. Under that, please write carboxylic acids have the following structure. Carboxylic acids have the following structure. And then start taking point form certain important details. First one, carboxylic acids partially dissociate in water. Carboxylic acids partially dissociate in water to produce H plus ions, and carboxylate anions, Take this down. Okay. Carboxylic acids have the highest boiling temperatures when compared with other organic compounds, when compared with other organic compounds, with a similar molecular mass. Okay, so now students, something to keep in mind is, if you take different organic compounds with similar molecular mass, if you take something like alkanes, more than alkanes, aldehydes and ketones will have a greater boiling temperature. If you take alkane with a similar molecular mass as well as aldehyde with a similar molecular mass, aldehydes will have a greater boiling temperature. Why? Alkanes only have London forces. Aldehydes and ketones have London as well as permanent dipole interactions. Is that clear? Right. But compared to aldehydes and ketones, alcohols have a better boiling temperature. Why? Alcohols have, apart from London forces, alcohols have what? Hydrogen bonding. Right? So therefore we have alkanes, we have aldehydes, ketones, we have alcohols. Then we have learned only about these guys, no? And then if you take carboxylic acids, they are above alcohols as well. Carboxylic acids can form a greater number of hydrogen bonding. Apart from that, they can also form permanent dipole along with London. Right? So it has higher boiling temperature. Now, further, there's another reason, that is smaller carboxylic acids. Smaller carboxylic acids, they are capable of forming what is known as a dimer. Right? So we call this dimerization of carboxylic acids. Right? So this is the carboxylic acid structure. Imagine this is a simple carboxylic acid. This is ethanoic acid. Right? So when you have ethanoic acid in the pure form without the presence of any other solvent, what happens is it produces this particular dimer. So you know there can be hydrogen bonds formed between hydrogen and oxygen. This hydrogen is partially positive, this hydrogen is partially negative. So this one also, there is a hydrogen bond that is formed. It should be nicely parallel. Okay, so then this will be forming a dimer. This dimer is quite strongly, two molecules are quite strongly attracted together. So they stay together in a single, as a single unit. They stay together as a single unit. So now this increases their what? Overall mass. Now there's one single unit is no longer this. One single unit is this entire dimer. So now they are heavier, larger, right? So therefore, this, although individual molecule has a smaller molecular mass, since they are acting as a single unit together, we can say this one is heavier and has usually a bit of a much higher boiling temperature compared to molecules with this simple molecular mass. Is that clear? They are somewhat cheating, they are staying together. So therefore their overall molecular mass tends to be a bit higher than what we see. Not tends to be, it actually since they are staying together, it is recorded to be a bit higher. Is that clear? Right. So take down another sentence under this. Smaller carboxylic acids undergo dimerization. Smaller carboxylic acids undergo dimerization when no solvent is present in the medium. That means when it's pure carboxylic acid form only, right? Due to dimerization, these carboxylic acids show higher boiling points. Carboxylic acids show higher boiling points compared to alcohols, aldehydes and ketones with similar molecular mass. With a similar molecular mass. Is that clear? Take this down. Okay, write dimer. And the blue color lines are hydrogen bond, students. That's a hydrogen bond. Is that clear? Okay, understood now? So these are hydrogen bonds. You can identify this as hydrogen bonds. Hydrogen bonds. The other thing is this. If you take a carboxylic acid molecule, students, right? This section of the carboxylic acid molecule, is polar. Dissolves well in water, forming hydrogen bonds. Obviously, the alkyl group, or the hydrocarbon section, is non-polar. Do not dissolve well in water. Therefore, we call this non-polar alkyl group section, or we say R group. You can write, therefore, when R group increases in size, solubility of solubility of carboxylic acids decrease. Is that clear? So students, carboxylic acids with larger alkyl groups do not dissolve in water. Small ones dissolve. For example, ethanoic, methanoic, they dissolve in water. Acetic acid, vinegar dissolves in water. No, vinegar is containing acetic acid. It dissolves in water, no problem. Is that clear? But if you take a look at larger acids, like let's say something like hexanoic acid, pentanoic acid, they don't dissolve in water. Small amounts dissolve in water. Majority of it doesn't dissolve in water. Is that clear? And the thing is, I will give you that note later on. First of all, take this down. Solubility of carboxylic acids. Solubility of carboxylic acids. And take this down. Are you done? Write down. Okay, right. Carboxylic acids with 1 to 4 carbon atoms. Carboxylic acids with 1 to 4 carbon atoms. Carboxylic acids with 1 to 4 carbon atoms dissolve well in water. Dissolve well in water. However, as the carbon atom number increases, solubility decreases. Then write aromatic carboxylic acids. That's a new point, important point. Aromatic carboxylic acids are insoluble in water and they precipitate out from aqueous mediums. As white color needle-like precipitate. I'll write some example reactions here as well. Example reactions. Now we learned about benzene's reluctancy to get oxidized. So therefore, students, if you have any carbon containing group like this, and if you add H plus KMnO4, it will directly turn into carboxylic acid. But the benzene ring will not change, undergo any change. Just the group that is connected here will turn into carboxylic acid. Even now, we know about aldehydes and ketones. Right? We know aldehydes undergo oxidation, but ketones never do. We learned that ketones never undergo oxidation. But that is not applicable to aromatic ketones. Meaning, if you have a ketone like this, this is a ketone, right? This will undergo oxidation. Is that clear? If you add H plus KMnO4, this will also undergo oxidation to form COOH. These are all white color precipitates. Right? These are all white color precipitates. Is that clear? So H plus KMnO4 is aqueous medium. So in aqueous medium, as soon as this is produced, it precipitates out as a white color precipitate. Is that clear? So take this down. Are we done? Can I erase these parts now? Okay. So now take reactions. You can write reactions. You can write under that reactions involving the cleavage of oxygen hydrogen bond. Cleavage of oxygen hydrogen bond. If you take any carboxylic acid, it reacts with the following easily. So we are talking about cleavage of this bond, right? So this can very easily be achieved by reacting with sodium metal, right? Can you remember any acidic? These are acidic. Whenever hydrogen reaction leads, this is acidic hydrogen. So you can see we store acidic hydrogen in many things. Can you tell me a few things that has acidic hydrogen in it? First one I think we learned was alkynes with terminal carbon or terminal hydrogen, right? It had acidic hydrogen. Alcohols also had acidic hydrogens, but very very minute. These two are very small in acidity, right? And apart from that, we learned what else have acidic hydrogens? Students? Phenols. And we learned about phenols. Phenols acidity was greater than phenol acidity was greater than alcohols. And now we learn about carboxylic acids. Is that clear? So usually the comparison is always between alcohols, phenols and carboxylic acids. Out of those, alcohols are the least acidic, then phenols are more acidic, and then finally carboxylic acids are the most acidic in organic compounds. In organic chemistry, when you're talking about organic chemistry, the most acidic is carboxylic acids, then phenols, then alcohols. Is that clear? So when you add sodium, you get this CH3, C double bond O minus, because H plus is left, and then we have sodium. Sodium will be there as sodium 1 plus. So they are ionic. So this acetate anion and sodium 1 plus ion is together, and then apart from that we will be producing hydrogen gas. So students, of course, if we are balancing this, two of them are needed to produce hydrogen gas. Is that clear? But I haven't written balance the equation here. I'm just trying to show you the basic equations that are taking place, general summary. So if I write 2 here, it will not be applicable for everything. So therefore I'm not going to write that. Is that clear? And then we can add sodium hydroxide. If you add sodium hydroxide, NaOH, it will easily react with NaOH as well and form CH3, C double bond O minus, Na plus, and H2O. So the OH minus and H plus here reacts to form water. Sodium 1 plus and the acetate anion will stay as an ionic compound. The other thing is we can react with sodium carbonate. Up until now, none of the organic acidic substances were capable of reacting with sodium carbonate, right? None of it. Phenols couldn't react, alcohols couldn't react, any of the acidic substances couldn't react with sodium carbonate. They didn't have enough of acidity to do that. But when it comes to carboxylic acids, they are acidic enough to do that. So therefore you are producing something like this, CH3. Again, the acetate anion will be produced along with sodium, right? And H pluses will be given to carbonate. H pluses and carbonate will produce carbonic acid, which is unstable. It turns into carbon dioxide and water. I have told you about this many a times. I'm not going to expand on this again, right? I might if I feel like you guys are now somewhat out of touch, but for the time being we'll move on. Last one is addition of sodium bicarbonate. It's the same as earlier, right? So then you are producing the same product, CH3, C double bond O, O minus in A, and then carbon dioxide and water. Now students, since I am a bit worried you can't remember what's happening, if you take carbonate ions, or even if you take bicarbonate ions, they are not that different, right? Only difference is this one has additional hydrogen. If you give them hydrogen atoms in the form of H plus, actually, if you give them H plus ions, not hydrogen atoms, if you give them H plus ions, what happens is they produce carbonic acid. They produce carbonic acid. Carbonic acid is quite unstable, right? They are very unstable. So they immediately break down. I will draw them together because I don't want to rewrite it again. So this breaks into carbon dioxide and water. It breaks into carbon dioxide and water. H2CO3, which is present in your fizzy drinks that you will drink most probably during the break. So they will have carbonic acid. As soon as you open it, carbonic acid that is unstable, so it dissociates, forming carbon dioxide and water. Is that clear? You drink a little bit of carbonic acid also, and then it dissociates in your stomach. So what happens? You get a burp, right? So that happens. Is that clear? Right, do you understand now? Okay, so take this down under OH1, the following reactions can be seen. You just take it down and that's about it. There's nothing further to be mentioned there. Feeling okay? All good? Take that down. Don't take the H plus, the carbonate part. You can leave that one out. I just want you to take this main summary. Next Monday, is it a holiday of some sort for you all? Huh? Are we done? Right. So these are the basic reactions that you see. Under that please write. Under that please write. Carboxylic acids have the highest acidity. Carboxylic acids have the highest acidity. When considering all the organic acidic compounds. All the organic acidic compounds. Alcohols are there. Greater than alcohols we have phenols. Right, greater than phenols we have carbonic acid. Right. I will explain to you why we say carbonic acid has a greater acidity than phenols. And then we have carboxylic acid. Greater than this, we have mineral acids. Mineral acids such as HCl, nitric, so on and so forth, right? So now, why did I say carbonic acid? Now students, carbonic acid actually has this, what do you call it, equilibrium, right? So plus CO2, CO3 2 minus turns into H2CO3. Okay, so only a strong acid, like very strong acid, can provide enough H plus to a carbonate to turn it into carbonic acid. Okay, so that means if you are trying to, let's say you take sodium carbonate and try to react sodium carbonate with acid, this reaction will happen, right? We will produce this, and then after that this will turn into, we know, carbon dioxide and water. That is a different story, right? But initially you need to provide H pluses to carbonate. Providing of H plus to carbonate cannot be done if the acid that we are talking about is weaker than carbonic. Is that clear? Only a strong acid, like let's say now these guys are weaker, they can't provide, but this one is a strong acid than carbonic acid, so it will provide enough H pluses to shift this reaction to the right hand side, and we get to this. Is that clear? So you haven't learned about equilibrium yet, but under equilibrium this will be much clearer to you. So only thing that you need to keep in mind is these guys are not stronger than carbonic acid, and that is why they cannot react with carbonates to produce carbon dioxide and water. Is that clear? So these ones are not stronger than this. Is that clear? Take this down, and in the sense the order, and then we will quickly take a small note down and we'll move on. Take this also down. Shall we write a small question down, students? I want you to be able to answer this question on your own. So I will ask you to think about phenols and answer this question, okay? So write down a small question. When a carboxylic acid releases H+, the produced carboxylate anion is relatively more stable than the carboxylic acid itself. So students, this is one of the reasons why carboxylic acids are acidic. The anion is more stable. Just like phenol's anion was more stable than phenol. Phenoxide anion was more stable than phenol. That's why it was releasing H+, right? So now, I want you to explain, write down. Explain why it is more stable. Explain why it is more stable using resonance structures. Can you please do that? Explain why it is more stable using resonance structures. I'll give you 2 minutes and I'll come and have a look at your answer. No need to use this. This carboxylic acid, students, a normal carboxylic acid would do. I'm asking you to think of phenol structure because we spoke about resonance there as well, and we explained something in phenol. You can use a R group instead of anything else. Right, this is the reason, students. So now, if you take a look at this, if the carboxylic acid is taken into consideration, when you are drawing another resonance structure, we can take the lone pair on the oxygen here and put it here, and the double bond between carbon and oxygen can be broken and the lone pair can go here. So at that point, we have an oxygen with a negative charge, oxygen with a positive charge. So having a positive charge on a very electronegative element like oxygen, oxygen is the second most electronegative element. Having positive charge there, it's not stable. Is that clear? Not stable. If you take a look at this, you can see it's the same thing actually. Even when we shift the like a lone pairs and draw a second resonance structure, it's basically the same thing. There's nothing changed here, right? Oxygen with a double bond and a negative charge oxygen, oxygen with a double bond and a negative charge oxygen, right? So in each of these cases, in the second scenario, there's no positive charge on a oxygen atom, only a negative charge on oxygen, which is going to be quite stable for a very electronegative element. Is that clear? So therefore this is more stable than this. So this anion is stabilized by resonance more than the carboxylic acid itself. Understood? So therefore, when it comes to the reaction that we see, right, we see this kind of reaction, we saw that earlier, that if you are talking about this, through resonance, this anion is more stabilized, so therefore the reaction will be proceeding more towards the right hand side. Is that clear? Through resonance, anion is stabilized more than the carboxylic acid. Right. So shall we take something down now? No? Okay, take this down, finish it off. Shall we? Write down the next heading. Reactions that involve the cleaving of carbon-oxygen bond. There are three main reactions, students. So I will give you an example like this again, so it will be easier. So we have this. Now today in this particular part we are focusing on cleaving of carbon-oxygen bond, this bond. Right. So the few easiest ones to remember are these. You can add PCl, we'll add PCl3 first. PCl3 can be added. So we form CH3, C double bond O and Cl here. This is referred to as a acyl chloride. Right? It's a acyl chloride. And apart from that, we form H3PO3, phosphorus acid. We can also form the same product by reacting it with PCl5. So there we produce the same product, but we will form POCl3 as a byproduct. and HCl. Our main interest is this, but we learn about the byproducts here as well, so remember those. I don't write the byproducts for everything, so if I write the byproducts, you need to remember those. Is that clear? But our main product is this. And the other one is quite an important one, so I'll talk about it separately as well. That is esterification, right? So we will add alcohol, CH3, OH, let's say methanol, and concentrated sulfuric. This one I will talk about it separately, right? So at that point you produce an ester. We discussed this under alcohols also. I don't know whether you remember. Didn't we? We discussed this under alcohols, right? Esterification reaction. I love how you guys are like, did we? Yes, we did, right? So under alcohol we discussed it under which topic? What was the topic? Now this is cleavage of carbon-oxygen bond and carboxylic acids. Under alcohols we discussed it under what type of topic? Cleaving of what bond? Oxygen hydrogen bond. Cleavage of oxygen hydrogen bond, right? So I'll talk about it again. So for the time being, please take this down. I don't have anything to explain here. This is quite simple, self-explanatory, but this one I'll have to talk about it separately. This is called esterification reaction. So I will give you a separate note on that, like a simple one, but I want you to first take this down. There's heat also needed, students. Right. So take a new subject, esterification reaction. Esterification reaction. Can someone tell me the name of that ester? Esters, when they are naming them, this is the main carbon chain, right? Carbon with the oxygen double bonded to carbon should be taken as the main carbon chain. So this section is a substituent group. So what kind of substituent group do we have here? Ethyl or methyl? Ethyl. So we write here ethyl, and then unlike in many other names, we normally don't leave spaces, no? But when it comes to esters, we do leave a space, right? Only when it comes to esters and carboxylic acid derivatives, we usually have these spaces, right? Ethyl space, and then how many carbons are present here? Altogether 3 are there, so therefore we write prop, and the suffix of esters is O8. O8. So this particular ester is ethyl propanoate. Is that clear? Ethyl, you have this section, the ethyl section, and this section is a propanoate section. Is it understood now? Take this down. So the condition should be here: concentrated H2SO4, concentrated H2SO4 and heat. Normal students, it's a reversible reaction, but when you are initially learning it, we can write it like this, that's fine. So for the time being, please take it down like that. And you need to realize that it's the carbon oxygen bond in the carboxylic acid that breaks, okay? And then the alcohol, you can see only the oxygen hydrogen bond broke. Is that clear? So alcohol's OR section connects to carboxylic acid's carbon oxygen double bond section. Okay, shall we? So under that, please write, this is also known as a condensation reaction. This is also known as a condensation reaction. Concentrated sulfuric acid acts as a catalyst in this process. Now students, we'll finish off carboxylic acids here. Okay, so the last part under carboxylic acids is this. Write down reduction of carboxylic acids. Reduction of carboxylic acids. Any carboxylic acid, you can write down any carboxylic acid any carboxylic acid can be reduced to its corresponding alcohol, with the use of lithium aluminium hydride. Take this down. Even aromatic carboxylic acids, okay, they are also getting reduced to the alcohol when you are adding lithium aluminum hydride and water. Usually we say acidified water, H plus H2O. Take all three down. Everything here you need to take down. Right? Under this, please write, unlike lithium aluminum hydride, sodium borohydride is not a strong reducing agent. Therefore, it cannot reduce carboxylic acids. Is that clear, students? Students, this comes in quite handy. You will see in certain chemical reactions, you need to reduce, let's say, aldehyde group, but you want to keep the carboxylic acid group the same. Is that clear? Then what can you do? you can add this. Carboxylic acid groups will not undergo any change, but the aldehyde groups will undergo change if you add sodium borohydride. But the carboxylic acid groups will stay unchanged. Nothing will happen to them. Is it understood? So this is a very good reagent because it is not reacting enough to reduce carboxylic acids, but it will definitely reduce aldehydes and ketones. Is that clear? Aldehydes will be reduced to its primary alcohol, ketones will be reduced to its secondary alcohol. Is that clear? Right. So students, we are done with carboxylic acids. Now there is something called carboxylic acid derivatives. I think we will get a little bit of, now still we have time for the break. So we will get a little bit of carboxylic acid derivative part also done, and we will move on. Right. So take a new heading, carboxylic acid derivatives. The reason why I am giving you these equations is because students, we will be able to do some questions after these parts. If you don't cover these parts, it will be difficult for me to give you questions. So if you take carboxylic acid derivatives, students, the first thing that comes into mind, we can write number one, right? Number one, acyl chlorides. Acyl chlorides. Or we say acid chlorides. Acid chlorides or acyl chlorides. Acid chlorides or acyl chlorides. So acyl chlorides are these: RCOCl. Now instead of a OH, we have a Cl. Can you remember how we produce these? We can produce this using what? Very easily, carboxylic acid. We add PCl5. You produce this, right? Now these guys are way more reactive than carboxylic acids. Right? They can't be even stored with water. Like if there's water in it, in the medium, they will immediately react with water to produce carboxylic acid again. They are quite reactive, right? So you can write under this, you can take this down. Right? You can take this down. Acyl chlorides are quite reactive compared to carboxylic acids. You can write the chloride attached to the acyl group, the chloride attached to the acyl group can easily leave in the presence of nucleophiles. Students, good example would be, right? Good example would be, now we'll write reactions. Reaction number one. So you can have, like you can write reaction with sodium hydroxide, right? Very fast reaction actually. So what happens is, if you put ROCl and if you add sodium hydroxide and NaOH, this becomes again carboxylic acid. This becomes again a carboxylic acid. Is that clear? So the carboxylic acid will react with the sodium hydroxide in the medium and turn into carboxylate anion. That's a different story, but this will easily happen. So further reaction can take place. Sodium hydroxide will further react with this to form the carboxylate anion. Right? Keep in mind, whenever an acid is produced into a basic medium, the acid will react to the basic medium. Understood? So we are reacting these two together and the acid is produced. But it is released into what? Basic medium. As soon as it is released into basic medium, it will produce a carboxylate salt. Now, the mechanism here is quite simple. You should be able to figure out the mechanism as well. Some of you may have already figured it out. Have you? Right? So if you take this carbon chlorine bond, this is partially negative, this is partially positive. So if you take the OH group, right, if you take the OH group, you can see this oxygen over here is having a lone pair. Actually there are 3 lone pairs, I will represent only one. This can be given here and the carbon chlorine bond can be broken and chloride ion can be acting as a leaving group. We say it is a leaving group and you produce what? Exactly. Simple, right? That's what happens. So simple. And this reaction usually happens faster. Students, most of the derivatives of carboxylic acids can be represented this way as well. Carboxylic acid derivatives. Now this is the carboxylic acid partner. But this group can be replaced with something else. So when we replace it something else, we have a carboxylic acid derivative. So we will call it this. Okay. So this section usually acts as a leaving group. It can leave in the presence of other nucleophiles. Right. So you will see many reactions where something comes here. As soon as it comes, the X group leaves. Right. So when it comes to carboxylic acid derivatives, this section is acting as a leaving group. Is that clear? That's what happened. OH minus came, Cl minus left. Is that clear? Take this down. So always keep in mind acid chlorides are more reactive than carboxylic acids, okay? Are you done? Second one, reaction with water. Reaction with water. Okay, right? Carboxylic acids react vigorously. Carboxylic acids react vigorously. Even with this it will react vigorously. But we can write carboxylic acids react vigorously with water. Not carboxylic acid. Carboxylic acid, sorry students, not carboxylic acids, acyl chlorides or acid chlorides will react vigorously with water. Now, actually students, the real funny part about this is, in most of these cartoons and all that, you have this acid sound that you see. Have you ever heard that sound, acid sound? Like they put acid into a flow, you hear this sound, right? So you think it's an acid that produces that sound? Most acids don't produce that sound. If you add acid to something, you don't have like this kind of burning kind of sound, right? But if you take acid chloride and add it to water, the reaction is so vigorous, as soon as acid chloride drop into the water, you hear this sound. The sound that you normally get from like cartoons when acid is added to something. Is that clear? So the reason I'm bringing it up is because to show that this is very vigorous. The reaction is very vigorous. With water it reacts immediately. So if you are trying to do a reaction that has acid chlorides in it, if you try to react with something else, if the medium has water, then you are not going to get the product you like. Is that clear? Imagine you are trying to do esterification reaction using acid chloride. If you have a lot of water in the medium, water will react with the acid chloride, right? So you normally prefer anhydrous mediums when you are reacting acid chlorides, because acid chlorides are very, very reactive with water. So reactions with water, H2O. So again we can directly write R C double bond O Cl will react with H2O to produce carboxylic acid and HCl. Now students, the mechanism here is not given to you, but we'll learn about it, right? Because the ones that are not given to you are also important, because you can then be asked about those things. Now what is happening here? I told you carboxylic acid derivatives such as these ones have these groups that are going to be leaving groups. So if a water molecule comes, now water molecule has lone pairs on it. Water molecules have lone pairs on it, right? So therefore students, a lone pair can come and attack, lone pair can be given to this carbon, and the carbon chlorine bond can break and chlorine can leave. So when that happens, you produce this. And there's a Cl group that left. Cl group that left. So again, Cl group has 4 lone pairs. I am only representing 1 because I need only 1 to show the electron transfer. Actually, if you take a chloride ion has 4 lone pairs. I haven't drawn all of them. Right. So what happens is the chloride ion will give electrons to a hydrogen, because here the oxygen is positive. After giving a lone pair to this carbon, this oxygen is going to be positive. So having a positive charge on oxygen is not very good. So we want to get back a lone pair from somewhere. So we like to break a oxygen hydrogen bond. So what we do is we break this oxygen hydrogen bond, and the hydrogen has been given 2 electrons from chlorine. So therefore everything is okay. We are producing carboxylic acid. We are producing a carboxylic acid. Now oxygen has no charge there. Everything is okay. And apart from that, an HCl will be produced. Is that clear? This mechanism is not given to you at the in the textbook, but there are so many other mechanisms that are like this that were taught to you. So you should be able to draw it on your own without my help. Is that clear? So little by little, get the hang of drawing mechanisms on your own. Take this down. There are other reactions of acyl chlorides, but I think I'll give you a break now after this. Are we done? Okay. So students, since there are other reactions also that we can do, but we'll take a small break, right? So now it's 11:10. We'll start the class again at 11:30. Okay. So take a small break and be here by 11:30, and we'll continue till we'll continue till 1 o'clock. And we'll take a small break. 1 hour break enough for you? Yeah. Right. So take a small break. I'll see you all again at 11:30. Right, shall we start? So students, apart from these reactions, apart from the ones that we just discussed, it shows other reactions as well. For example, a good way to compare the fact that these are more reactive than carboxylic acids is, if you take an acyl chloride, and react it with any alcohol, right? It could be aromatic, or basically it could be phenol or normal alcohol or acetic alcohol. So if you react with an alcohol, let's say just a CH3 group here, these will be removed and be leaving as HCl, and these two will connect together. The thing that proves that this is more reactive than carboxylic acid is, if you remember correctly, carboxylic acid required a concentrated sulfuric acid as a catalyst when this reaction was taking place. When your ester is formed, carboxylic acid reacted with alcohol in the presence of a catalyst. Apart from that, we needed to heat it a lot, usually to slightly high temperatures, right? But here we don't need to do that. We just need to mix the carboxylic acid, we just need to mix the acyl chloride with the alcohol. That's it, right? Then the reaction will take place and this will be produced. Is it understood? Okay. Write down reactions with alcohols. Reactions with alcohols. You can write acyl chlorides will react with alcohols under much milder conditions, compared to carboxylic acids. And will produce esters. You can write concentrated sulfuric catalyst is also not needed. Concentrated sulfuric catalyst is also not needed. Is that clear? Right. So now we are done with this part. Take this down. We have another reaction that we need to do. So we are done with acyl chlorides then. can write the last reaction under this. Reactions with amines and ammonia. Reactions with amines and ammonia. Okay, students. So any acyl chloride can write any acyl chloride can react with ammonia, primary amines and secondary amines to produce amides. Example is this. You can take these examples down. So I'm going to use the same thing here because it's easier for me, right? So we will react this with ammonia, right, students? Although keep in mind this is one very important point. Although we highlight the hydrogen atom and Cl here and say okay, this is the reaction that is taking place, actually what happens is first the ammonia, the lone pair on ammonia is attacking this and the Cl leaves. Is that clear? And then you should be able to write the mechanism. I'll get you to write the mechanism. That's a good thing, right? Good thing. So first write the product. I will give you a separate question about this, students, so don't worry. First write the products. So this is ammonia. Right, so this is a primary amine. So this is a primary amide, right? So write these down, these reactions. Oh. Exactly now? Done. So now, what is happening here is, although we highlight this hydrogen and Cl and show we are leaving, there's a much more complicated mechanism there, right? Not just hydrogen comes into contact with Cl and they are like joining, and nitrogen and carbon connecting. No, there's a mechanism here. But you need to understand what the mechanism is. We highlight these and show that they are leaving for our convenience, so that we can easily identify what the product as well as a sub byproduct is. But there is a underlying mechanism. So let's see whether you know the underlying mechanism. Right, write a small question here. Draw the mechanism of the following. Draw the mechanism of the following reaction. I want you to be very confident with mechanism, students, because mechanisms are very important, okay, when you are learning about this kind of thing. So let's say we have this acyl chloride, okay. First of all, can someone name this acyl chloride for me? We have learned naming some time earlier. So this is referred to as, the suffix of acyl chlorides is OYL chloride. This is the suffix. Everything else is the same, students, from here onwards. This is the suffix. What is the name of this acyl chloride then? How many carbons are present here? 3. So then we have, and carbons have only single bonds, right? So this is prop, and what is the suffix? OYL chloride. So this is what? Propanoyl chloride. Ones with 2 carbons would be ethanoyl chloride. Ones with 5 carbons would be pentanoyl chloride. Is that clear? Simple. So now I want you to show me the mechanism between this reacting with an amine. Right? So you haven't learned about amines in detail yet, but we have encountered amines. At least now we know there's something called amine. So basically, students, an amine is a substance where some hydrogens of the ammonia is substituted by alkyl group. Okay, some hydrogen of the ammonia is substituted by alkyl group. Here one alkyl group substitutes one hydrogen. Okay, 2 other hydrogens are there. So if only one alkyl group is present connected to the nitrogen, this is called primary amine. If there are 2 alkyl groups, it will be a secondary amine. If there are 3 alkyl groups, is a tertiary amine. Is that clear? So amides, I gave you earlier in the diagram, you could see I spoke about amides. So amide also had a nitrogen group. I don't know whether you remember. So take a look at, I will talk about that as well. So amide is something, students, that looks like this. This is a amide. So a carbon oxygen double bonded group is directly bonded to a nitrogen. This is not a simple alkyl group. So then therefore we can't call it amine. This special category is referred to as an amide molecule. Amide, right? These are simple, like alkyl group, tiny alkyl group is connected here. So therefore this is called amines. These ones, when you have a carbon oxygen double bonded group directly bonded to nitrogen, it is referred to as a amide. So if the amide has 2 hydrogens freely, it's a primary amide. Is that clear? If it has only 1 free hydrogen, it's a secondary amide. If it has no hydrogens at all in it, it's a tertiary amide. Is that clear? Now you know this primary, secondary, tertiary thing, right? Primary alcohols were looked at, primary, secondary, tertiary alkyl halides were looked at, carbocations were looked at, right? So now we talk about amines and amides. Okay? Same thing. Amides, we don't dive into it too much. Actually, amines, we'll be learning about it in detail in the next part. So today I'm assuming after this I'll be doing some questions, and after that when we start the next session, I will be able to finish off amines, and we'll be able to finish off organic chemistry. Is that clear? So from there onwards, we'll have a very good question covering session, and after that we'll move on to the next lesson. Okay. So I want you to write the mechanism for this reaction. I want you to write the mechanism for this reaction. Start now. Does someone know the name of this lane, students? What is the name of this lane? Is it Veera lane or some other name? No idea? This lane? Sisuji lane? Done? Where do you all go to eat here? Where do you all go to eat here? You bring lunch? It's trying to find a place. So now, let me ask you this, okay? This already has a lone pair, right? So when anything that has a lone pair is a, what do you call it, can act as a nucleophile, right? This one, as it is, can act as a nucleophile. So what happens is, can you remember water addition? So water, we didn't initially break these bonds now. Water had a lone pair. At least one lone pair is enough. That lone pair attacked. And then when oxygen became positive, then only the oxygen-hydrogen bond broke. Is that clear? So we don't need to initially start by breaking these bonds. This doesn't happen actually. It directly attacks here because of the partial positive, partial negative charges on this bond, right? Carbon is partially positive. This initially happens, and then later on only the nitrogen-hydrogen bond will be broken, right? There's a chlorine lying around and then they come and attack. Do you understand? Pretty similar to the previous mechanism. Right, so very good. Initial start is correct. Correct. Very good, very good, very good. So it's correct. But be careful when it comes to drawing this arrow, okay? I know this is the full head, but it looks like a half arrowhead. So if someone has a, like imagine the one who's marking didn't see it that way, you'll be losing a mark. Yes, good. But this nitrogen, after donating the lone pair, the nitrogen is positive. You need to show that. And after donating, now when this donation happens, this nitrogen hydrogen bond breaks. That electron transfer should also be shown, and then there will be a lone pair here. Okay. Navin, can I see yours? Give it a try. I will see yours also. Why did you attack the? Okay, try to go back to the water reaction with SI chlorides. I have given the mechanism. So this is pretty similar to that, right? This is wrong. I will start drawing the structure. Now I will give you some pointers because this is very important that you pick up on these cues, right? So I will give you some pointers. First, this has a lone pair. It can be donated, right? But why in the world would it donate? What is the reason for it to donate it to something else? It will donate if there is a carbon atom that is electron deficient, right? So we need to show that there is a carbon atom that is electron deficient. So for example, this side is partially negative, this side is partially positive. And even if you take this oxygen carbon bond also, that is also polarized the same way. Carbon is partially positive, this one is partially negative. So carbon is quite electron deficient. So it is weak, or not weak, it is like more prone to attacks from electron rich groups. Is that clear? This guy doesn't have electrons, someone has electrons, so therefore there can be attack from that. Is that clear? So yes, this attacks. And this bond, which is already quite polarized, can break and the bond electrons can be given to chlorine. So chlorine will be going off. So when you have that, you get this CH3, CH2, C double bond O, and then we have nitrogen here connected to CH3 and hydrogen here, and there's a lone pair here. Sorry, no, lone pair, I'm sorry. Nitrogen has two hydrogens. I forgot. Nitrogen has two hydrogens. Now, earlier nitrogen had altogether 5 electrons around it. If you count now, nitrogen has only 4 electrons around it. So nitrogen is positive in charge. And you can also argue nitrogen gave a lone pair to form a bond. So therefore nitrogen anyway going to be positive in charge. So let's say there's a Cl minus ion. Now this is the bond electrons that Cl got. So now Cl is negatively charged. So Cl minus ions can donate electrons here, because if you take a look at this bond, hydrogen is partially positive, nitrogen is partially negative. Nitrogen is carrying a positive charge, true, but at the same time we want the positive charge of nitrogen to be gone, meaning we want to take a bond electron pair back onto nitrogen as a lone pair. So we like to break a bond here and take those electrons onto nitrogen. Nitrogen carbon bonds cannot be easily broken, but nitrogen hydrogen bonds can. So what usually happens is chlorine come and give its electrons to hydrogen to form a bond between these two, and hydrogen can now break hydrogen nitrogen bond easily, and the electrons are given to nitrogen. Electrons are given to nitrogen. So at that point you will be forming this. clear? So that is the final product. Apart from that, of course, HCl will also be produced. Is it understood? Please try to get to the hang of this. Try to get the hang of this. Otherwise, it will be difficult for you when like a new type of mechanisms are given to you, or when a new molecule is reacted with something else and they are asking for the mechanism, you will not be able to figure it out. So again, randomly no bond will be broken. If a bond is broken, there is a reason for it. For example, here you will not be breaking these bonds easily. Like, you know, there is a reason for whatever the bonds that are broken. So automatically this will not break and start the reaction, right? So then what is the reason for the reaction to initiate? There's a very electron deficient carbon atom here. You can see it's partially positive, right? It is more likely to be attacked by electron rich species. Now this guy is electron rich, it has a lone pair. So it will start attack here and the carbon chlorine bond will break. Is that clear? So all these carboxylic acid derivatives have these leaving groups. When something comes in, they leave. Is that clear? So this guy is the leaving group. Is it understood now? Right. Okay. Right. We are done with acyl chlorides. That's the first molecule, first derivative. Then take the second derivative, number 2. Second derivative, esters. If you haven't taken this down, you can take it down. I'll erase the top bit. Second one is esters. Done? So if you take an ester solution, ester will look something like this. I will draw a simple ester here. Now esters are fascinating molecules, right? These guys have a very nice smell, characteristic smell, fruit smell actually. Fruity smell will be there. When you produce these things in the lab, the entire lab smells like you know, very nice. It's like fruit smell, sometimes vintaginous smell, pear smell. I haven't seen one with mango smell, but grape smell, pear smell, banana smell will be there, right? So again, the carboxylic acid section, this part is the leaving group. Is that clear? This section is the leaving group. Okay. So first of all, under that, take an example, ester example. And after taking it down, write down a new heading: hydrolysis of esters. Hydrolysis of esters. Can write, esters can be broken down to its constituent carboxylic acid, and alcohol through hydrolysis reactions. There are two main types of hydrolysis. First one, acidic hydrolysis. Second one, alkali hydrolysis. So I will give you a nice breakdown of what these two things mean. Right? First one, acidic hydrolysis. Now students, first of all, what is the meaning of the word hydrolysis? Hydrolysis. Hydro means water, lysis means breaking. Meaning we are adding a water and breaking this bond. With this particular bond that is present here is called the ester bond. That is what produced the ester, right? So this ester bond is going to be broken, and we are breaking it by attaching a water molecule. So we take a water molecule, some part of the water molecule goes into the carboxylic acid, the other part goes into hydrogen. Can you remember when we were forming the carboxylic acid, when we were forming the ester, can you remember water molecule was removed? Now we are taking that and we're putting it back, right? So that is called a hydrolysis reaction. So now in a hydrolysis reaction, again, this is also catalyzed by sulfuric acid. So sulfuric acid is a catalyst for the forward reaction as well as the reverse reaction. So if you take something like this, I will draw it in the following manner. CH3, CH2, C double bond O, OCH3. If you add Conc H2SO4 and heat, right? So there's water also present, obviously. At that point, actually I will write water here as well, plus H2O. Then this will turn into CH3, CH2, C double bond O, OH. Apart from that, you will also have an alcohol produced. So you are producing the relevant carboxylic acid and the alcohol. Easy, right? So in acidic hydrolysis, we produce these two, right? So that is something to keep in mind. Apart from that, you will note these things: carboxylic acid and alcohol is formed. I'm writing this for a reason. You will see why when I'm talking about the other one. So then we have alkaline hydrolysis. So students, if you take the same compound, if you take the same thing, CH3, CH2, we take the same thing. But if you add sodium hydroxide, what you get is two different products. Same thing, but you are not getting the product that we got here. Instead of the carboxylic acid, what we are getting is a carboxylic acid anion with sodium. So we can say a carboxylate salt is produced. Is that clear? Now why is this? Now we do the hydrolysis process. We are adding water here and we get to this. We actually produce this. But this is released into what? A basic medium. So this is very reactive with the base, no? So they will react to produce what? A salt. Is that clear? Like, you do all this reaction and you produce a carboxylic acid. As soon as you produce a carboxylic acid, you release it to what? A base. Right? It is produced and it is exposed to base. So sodium hydroxide will quickly react with sodium hydroxide. And will produce what? A carboxylate salt or carboxylic anion along with sodium. Right? Sodium 1 plus actually here. Is it understood? So therefore we don't get the carboxylic acid here. We get the alcohol because alcohols don't react with sodium hydroxide. but we get the carboxylate salt. Is that understood? So here we say carboxylate anion or salt and alcohol is produced. Is that clear? To obtain the carboxylic acid, we need to acidify the medium. Meaning, students, if you want to convert this into something like this, after getting this product, we take a whole bunch of acid and we add acid here. So we neutralize the base, and then after that we give H pluses to this. We can push H plus to this. So when you give H plus to this, we produce carboxylic acid. Is that clear? So to the anion, we have the anion here. Let's say if I take the anion, carboxylic acid anion, and if I give it H plus, it will turn into, this reversible reaction, it will turn into carboxylic acid. Is that clear? So what we are doing is, after getting here, we neutralize, we add a whole bunch of acid so that it gets converted into the carboxylic acid itself. Is that clear? So something to keep in mind. This is a MCQ question that they usually ask. They talk about hydrolysis and then they ask what is the product of sodium hydroxide reacting with this. Some of you forget that the hydrolysis does not produce carboxylic acid when you are adding sodium hydroxide. Some of you will directly write that as the answer. That is wrong, because you produce this. Is that clear? This MCQ is there. So anyway, under that point, can you please take this down? Are we done? Are we done? Yeah. Write a new reaction. Reactions with Grignard's reagent. Reaction with Grignard's reagent. Now, unlike any other aldehyde or ketone, this is not aldehyde or a ketone, this is different. This reacts with Grignard's reagent in two stages. Two stages. So now, for example, you can first of all write down a small sentence. Esters react with Grignard's reagent in two stages. Right? So I will write it in the following manner. So what happens is, students, if you add something like CH3 MgBr, now this is the Grignard's reaction in dry ether, what initially happens is this CH3 group can get connected here. Right? CH3 group can get connected here. So basically, students, I don't know whether you remember when you talk about aldehydes and ketones, I said this bond electron pair can easily be donated, right? And therefore this section acts as a nucleophile. Now what do we know about acid derivatives, carboxylic acid derivatives? We learned carboxylic acid derivatives have this section that is a very good leaving group. Can you remember that? I told you this is esters are carboxylic acid derivatives. So if a nucleophile comes, right, if a nucleophile comes and initiates an attack here, this part will be leaving. Can you remember that? So when it comes to CH3 MgBr, or when it comes to any Grignard's reagent, Grignard's reagents are acting as good nucleophiles. Why? Because these bond electrons, they are acting as they are very easy to be donated to something. So this section, it is acting as a nucleophile. So this can easily be donated here, and this section will easily here. Is that clear? So the magnesium bromine part will be also removed. That's something to keep in mind. So what happens here is this CH3 connects here, so we form CH3. The reason why I'm using different alkyl groups is that you understand what attached where. So this section is still intact, no problem there, but this bond was broken, and in place of that we are attaching CH3. Apart from that, the MgBr part is now connected to this. So we have CH3, CH2, O, MgBr. Is that clear? That part is there, but it's useless. We don't have any use for that now. Is that clear? So this is what we like. So this is a ketone, and you know ketones undergo Grignard's reactions very easily, right? So what happens? The ketone will undergo another reaction. So we have CH3, CH2, C double bond O. Now we have produced this ketone. The ketone will undergo further reaction with CH3 MgBr dry ether. You will produce CH3, CH2. See here we have O will be produced, O will become an OMGBr section, and you will have this CH3, and this section will again connect to the same carbon CH3. So basically this section attacks here, and this O becomes a OH, not OH, OMGBr part. If you want to convert it to an OH, you can add H plus H2O. So then it becomes this CH3, CH2, COH, CH3, CH3. So this is we are producing a tertiary alcohol. A tertiary alcohol will be produced. Is it understood? Simple as that. So these are the two stages that we produce. So very first reaction is, now we can't stop the reaction here, students, okay? No, we can't stop the reaction there. It continuously happens. Why? As soon as that is produced, the medium has more CH3MgBr. So it will react with that to produce this. But after the reaction has gone for a while and you produce mostly this, then we add water. When you add water with H plus, you get the alcohol. Is that clear? So take this down. Hello. Shashika, मैं done. Okay now? Okay. I will give you the last part for esters after this. So the last reaction is reduction of esters. Can you please write last section, reduction of esters. So students, if you take any ester, now I am taking this particular ester for a reason, students. So you can see what happens to the carboxylic acid group and the whatever the alkyl group in the ester, you can see that very clearly there. So if you react this with lithium aluminium hydride, we know when lithium aluminium hydride is used, right, we use water as well after that, H plus H2O. Then this section becomes, actually this breaks and will form two products, and both the products would be alcohols. This section also turns into an alcohol section, and this part will also turn into an alcohol section. So you're forming two alcohols. Is that clear? So if you want to break this in one go and turn it into an alcohol, we can directly add lithium aluminum hydride. You don't need to do acid hydrolysis first and then add lithium aluminum hydride. You don't need to do that. You can straight away break them and turn it into alcohols by adding lithium aluminum hydride and water. Is that clear? Right. So take this down. Right, sorry about that. So, are we done? Yes. Okay. Now, we are done with all the reactions revolving around esters, carboxylic acids, and acyl chlorides. So, all of those were derivatives of carboxylic acids. Now, there's one more, but I'll show you something again. So, again we learned, if you take a carboxylic acid, right, we can have this section replaced with something else. So we can have something like acyl chloride. These are derivatives of carboxylic acid. If you remove this section and have this is a derivative of carboxylic acid. That is referred to as acyl chlorides, right? And then we can have esters. CH3, C double bond O. Here we have again OR group or some sort of alkyl group. Again, this is a derivative of carboxylic acid. And if you produce an amides, right, if you have a nitrogen group, NH2, that is also a carboxylic acid derivative. So we looked at these two, we didn't look at this yet. And we also learned all of these carboxylic acid derivatives are leaving groups. When a nucleophile comes and attacks, they leave. Is that clear? So they are going to be leaving groups. So take a new heading, reactions of amides. Reactions of amides. We don't talk about it much, students, so I'll give you just, there's only two reactions, okay? There are only two reactions, I'll directly write them down. We don't talk about it much, but you need to know, right? So if you take any amide, I will write an example. I don't want to like R, I don't like R much. So I normally give you these type of examples. If you take an amide, you can react with it sodium hydroxide. What happens here is, students, hydroxide ions are there. I told you, no, hydroxide ions are nucleophiles. Come and attaches here. Then what happens? The amine group leaves. Is that clear? Amine group leaves. And then you produce this CH3, CH2, C double bond O, and here we will have OH. But this carboxylic acid that is produced will be released into what? The sodium hydroxide medium. Sodium hydroxide medium and carboxylic acid will react. So therefore you don't get this, you get this. Is that clear? Do you understand? We get a carboxylate anion. Is it understood now? Right. So this is what we get, and apart from that, ammonia will be produced. So this is one reaction. The other reaction is, again we can react this with lithium aluminum hydride. Now you have some sort of knowledge about the types of reactions that are normally happening. Guess and try to get to the answer that is here. I want you to give it a try. Right? Take a second and do this reaction. Now I want to show you, it's like, you need to memorize these things. I will tell you why after you guess. If you please do it this way, if you are guessing and writing a product there, write it with a pencil. Most likely you will have to erase it, right? So guess and write the product, but you will write, I am expecting you to write it with a pencil. And apart from sodium, the product I told you, ammonia will be produced here. I told you this. Write it also. And here the product, try to write that down. Did you write this? CH3, CH2, COHH, NH2. Did you write this? Did you write this? If you wrote this, it's wrong. That's why I asked. Did you write this? No, right? So normally we saw something like this getting formed all the time. But actually what's happening is, in this case, this group, in the presence of lithium aluminum hydride and diether, sorry, I forgot to write this, diether, this section becomes a CH2 group. right? So basically you have it like turned into a basic CH3 CH2 CH2 NH2 molecule. Is that clear? Right. So take that down, and I'm going to move on to questions now. Quickly take this down. Those are the only reactions under amides that you learn. We don't learn many reactions under amides. We learn about this and we move on to the next theory part. So the next theory part, or the last lesson in organic chemistry, is a very short one. We'll be talking about it after the break today. But before we go to the break, we will do some questions. Okay? We'll see whether you all remember how to get to, like, answers. Can I erase this? Are you done? Yeah. Right. So let's do something nice. Right. Now don't panic, okay? So when you see questions like this, it's a simple question, like you think it's a very difficult thing to do. But it's not. It's very easy. I will tell you this much. You will use a lot of equations you just learned today. Do this one, please. I'll give you 5 minutes or 3 minutes to get this done. If there's anyone who's done, let me know. Anyone who's done? No? Huh? So we did so many reactions today. Take a look at this. So I will ask you these questions. If you can answer these questions, that means you can get to the answers. First of all, is the CH3 group here, is it a very reactive group? Can we add things to it easily? No. Can we work with this to turn it into this? No. So this has to go. It has to turn into something else. That's clue number 1. And this NH2, right? Can we just connect a NH2 group to something like that? No. So we saw ammonia reacting with certain things today. What were the things ammonia was reacting with? Right? What were the things ammonia was reacting with? Go check your previous equations. Ammonia was reacting with certain things. What were they? Huh? Acyclorides, correct. So yeah, I have helped you now. I have helped you plenty. I'll give you a final clue. Very last equation we did today will be used here. Good. I believe that's enough time. So let's take a look at this question, students. Now students, this is usually not a very like useful group. It's like, you can't add a chlorine here also with a lot of control. Like if you talk about halogenation of alkanes, and if you try to add chlorine and UV radiation and try to get a Cl here and do that reaction, it will not be very successful. So therefore students, we are not going down that path. Right, because when it comes to the chlorination of alkanes, it's not going to be producing only the product we want. So what we can easily do is, we can convert this into a carboxylic acid. How can we convert this into a carboxylic acid? Oh, forget about that. Before, if you can't approach from that angle, we can talk about how to get nitrogens onto a carbon. So we saw nitrogen connecting into molecules through acyl chlorides, like he said earlier, right? And acyl chlorides can easily be reduced with the use of lithium aluminum hydride. If acyl chloride after turning into amide is reduced, when amide is reduced, you form just amine. This is amine. Earlier also, the last equation we did, amide got reduced to amine. So students, we could have produced an amide first. We could have produced an amide first, right? Carbon here, this here, NH2 here. So we can add one lithium aluminum hydride, 2, we can add H plus H2O, and we are getting this. Okay. So now how do we get here? We can get here also quite easily. If you had a acid chloride or acyl chloride, right? If you had acid chloride or acyl chloride, you can add ammonia. Actually, we normally add concentrated ammonia. What happens is NH2 group will be attached here, Cl will be leaving. Cl will be acting as a leaving group. Right? So easy. So now how do we get to a acyl chloride? We can first convert this into a carboxylic acid group by adding H plus MnO4 oxidizing agent. So it will turn into carboxylic acid. Carboxylic acid, COOH. And from this to this, we can easily do our conversion by adding PCl5. Is that clear? Simple reaction. So always, this is a very important reaction, students, okay? This ammonia addition to acyl chloride or an amine reaction with a acyl chloride, amine and acyl chloride, also very important, right? Keep in mind, I might give a question next on that. Ask yourself how to get this part here. I'm pretty sure you guys are asking yourself that question a lot, but then you're not properly thinking, like you're not searching your theory parts, like, okay, what were the reactions that got nitrogen? Like, so then you have to ask yourself, nitrogen contained reactions, what were they? Acyl chlorides reacting with ammonia or acyl chlorides reacting with amines can get us there, right? So those kind of reactions are there. And then you learn about certain other type of reactions where nitrile groups can be reduced to form an amine. That is also there, right? That you will learn after a while. Now today we'll be learning that, right? Is that clear? Now are we okay with this part? Right. So take a new question. Complete the synthesis in the following scheme of reactions. Complete the synthesis in the following scheme of reactions using only the reactants provided below. Using only the reactants provided below. Past paper question. So the reagent should be written here. This is exactly how they have given it, right? So final product is this. So there's a reagent that you need to draw here, right here. Reagent here as well, but they have helped you out a little bit here. They have written 1 plus 1 comma. So 1 and 2, not 1 plus 2. So this reactants are Mg, dry ether, lithium aluminium hydride, sodium borohydride, CH3CHO, concentrated ammonia, water, dilute sulfuric. So students, does that mean you have to use all of these? Anyway, no. It's misleading here. Two of the same thing. But this will not be able to reduce a carboxylic acid. This will be able to reduce carboxylic acid. So while keeping that in mind, yeah, you can get a start. You can see here 1 and 2. Remember, there are certain reactions that we do in 2 steps, right? What are those? We have done like so many questions now. You would know what those kind of reactions are. Like greenhouse reagents, we normally do in 1 and 2 steps sometimes. And the other one is what? Reduction, lithium aluminum hydride, correct. I will help you out here a little bit. This has a lot to do with acyl chloride's reactions with ammonia or amines. This reaction has a lot to do with acyl chloride's reacting with ammonia or amines. Is there anyone who's done? Okay, I will help you out now. I think some of you are stuck, so I'll help you out. First of all, it's very simple. Now today we learned about this just a little while ago. Listen, pay attention. Identify the product. What is the product? We have this same section here, and we have what is connected to that? An amine group, right? Amine means nitrogen connected to alkyl groups. So amine was connected here. So the most probably the final step would be amine connecting to the carboxylic acid group. So we learned carboxylic acid group, although they can directly react to the amine, normally those reactions are not very strong. So therefore, what did we do? What type of carboxylic acid derivative reacted with amines? What type of carboxylic acid derivative reacted with amines? Acyl chlorides. Acyl chloride reacts with amine. Okay, so we know that. So now that means I need an amine and a acyl chloride. Acyl chloride can easily be produced here. No? Now for example, I can have there is PCl5 given. I can add PCl5. Then what do I get? An acyl chloride. Now nowhere here they have given this amine that we want. It's a problem. The amine is this section. Nowhere here we have been given that amine that we want. So maybe this path is producing that amine. You understand? We have the alkyl halide. So not alkyl halide. We have the acyl chloride. And maybe this path is used to produce the amine that is needed to react with this acyl chloride. Is that clear? Now I have helped. Please produce the amine. We did that a little while ago. Similar reaction. We did that a little while ago. Similar reaction. Sorry? There's no PCl5. Huh? Oh, sorry about that, students. My God, I am sorry. It's actually one of the first things that is given in the question. I'm sorry, I haven't included that. That's why you were stuck. I'm sorry about this. Right. I can't blame you then. PCl5, water is there. Okay, everything else is there. If you are held up due to that, then that's okay. What is this? No, this one? No, don't add mg right. Good. Exactly correct. Good. Answer is correct. Can I see yours? Very good. Yes. The last one, what did you do? There's no need to add sodium hydroxide. You just have to mix the two together. No need to add this. Okay. But other parts are correct. Very good. Now, I will not do the question completely, but I'll ask you this question. Listen. To produce this particular amide, this is the amide, so we have to have an amine reacting with the acyl chloride. So we know that there's this acyl chloride that we need, right, which we have already produced, and we need an amine. The amine that we need is this, right? Amine that we need is this, and we know this hydrogen along with the chlorine will react and get removed, and this part gets connected to the carbon here. So now we need to produce this. Now we learnt a little while ago how to produce amine through a acyl chloride. So what you will add? Concentrated. Now the last question we did concentrated ammonia. So then what happens is you will produce an amide. You will produce an amide. Right? We did this last. Actually, the last question that we did. And the amide can be reduced by adding lithium aluminium hydride in dry ether, and then we can just add water, H2O. H plus H2O is better, but H2O is also fine. Is that clear? So then what you produce is CH3, CH2, NH2, which is this, right? The thing that we wanted. So if you add this and this together, no need of any reagents now. You mix this and this together, produces. Is that clear? So those are the basic reactions that you should be familiar with under this lesson. Okay. So this entire question was from our lesson today, what we did, no? So we'll take a look at a few other questions as well, but students, I'm having this need to complete the organic lessons. The next lesson, the amide and the amine section, is going to take about 2 hours. We'll be finishing them off, and we will we'll start some questions after that. Okay, I think some other students will also join us. So we will do that after the break. Okay, so take a small break. Shall we start at 2:25, right? 2:25, we'll start the next class. We'll go till 6. If you're feeling too tired, let me know. We will then wrap it up around 5:30, right? But I don't think it will be a problem. You can stay. I'm expecting you to stay. Students, one more thing. Next week onwards, I'm planning on having again this same class. Try to come and try to make sure that others come also, otherwise it will not be fruitful. Okay, I'm traveling all the way from Malabar. It's difficult for me to come early in the morning, but I want to still have this class. So try to get others to join as well, right? So we'll have a break. We'll start at 2.